When BGP makes its path selection decision, it can be a lot more involved than OSPF or EIGRP. OSPF can simply say, hey, let's look at the bandwidth and calculate the cost based on the bandwidth. We determine the shortest path to the destination network using the Dijkstra algorithm, and we go with the lowest cost path. EIGRP by default only considers bandwidth and delay. However, BGP can take several different things into consideration, and I've got all of them listed for you here on screen. This is a comprehensive listing, and it's more than you might see in some documentation because some of this deals with more advanced configurations, such as route reflectors or setting up multipath BGP. But I wanted to show it to you so you could have a comprehensive listing, and then later in this video, I'll point out the most important path selection parameters that you and I might deal with on a day-to-day basis as we try to influence BGP to pick a specific inbound route or an outbound route. But let's go through the comprehensive listing first, just so we can be exposed to that. The path selection parameters are listed top to bottom here on screen in order of preference. And the first one that we see is weight. This is a Cisco-specific parameter, and it's locally significant to a router. In other words, it doesn't get communicated to our neighbors. As a route comes into our router from a neighbor, we can stamp it with a weight. We could say that routes coming in from one router or one neighbor have this weight, and routes coming in from this other neighbor have a different weight, and a higher weight is preferred. That's a really common way to influence our outbound path selection decisions. And if we have more than one path to get to a destination network, we can go with the routes that have the higher weight and came from a specific neighbor. Another parameter that's commonly used for outbound path selection decisions is local preference. Now, this is not Cisco specific. And with local preference, a higher value is preferred, but this value is not locally significant to a router. It gets communicated with all other routers within an autonomous system. And next we're asking, from where did this network prefix originate? We're going to prefer a route that was originally advertised using the network statement, or a route that was redistributed into BGP. Those route origins are going to be preferred as opposed to a route that was injected into BGP using the aggregate-address command. Next up is the AS path length. This is the number of autonomous systems that are in the autonomous system path, or the AS path attribute, that shows the listing of autonomous systems that we need to travel through or into in order to reach a certain network prefix. Let's say that our BGP topology table tells us that we've got two different ways of getting to a specific network prefix. Well, BGP can prefer the path that has the fewest autonomous systems listed in the AS path attribute. Next is origin type. Was the route learned by BGP from an IGP, in other words, an interior gateway protocol like OSPF, or was it learned from an EGP, an exterior gateway protocol like BGP? Or do we have incomplete information? The origin type of I for IGP, that's preferred over an E for EGP, and that's preferred over the question mark for incomplete information. Up next, we have the MED, the multi-exit discriminator. This is commonly used to influence inbound route selection, such as when we're trying to influence routers out on the internet to use a specific ISP when they're coming into our network. We apply this parameter to the routers in one autonomous system to influence decisions in a different autonomous system. Here, the lower MED is preferred. And if everything is still a tie, we look to the paths attribute, where an eBGP path, that's a path between autonomous systems, is preferred over an iBGP path, that's a path within an autonomous system. The next tiebreaker is the next hop IGP metric, where we look at the next hop address and ask, what is the lowest IGP metric? Maybe we're running OSPF as our interior gateway protocol. If the different paths that we have to select from have different OSPF metrics to get to the next hop address, then we can go with the path with the lowest OSPF metric. Then we ask if we're enabled for BGP multipath. Do we need to have multiple paths injected into the routing table? If we still haven't selected a best path, the search continues. And the next tiebreaker is the age of the eBGP route. Which one is the oldest? And the oldest one, that's the one that's preferred. It's older and wiser, we assume. If we still have a tie, we're going to go with the lowest router ID. Specifically, we're asking which neighbor has the lowest router ID. The next parameter deals with route reflector BGP configuration. If we do have that type of configuration, we can prefer the route with the minimum cluster list length. Now, that's not something we need to be concerned about here at the CCNP level. We'll leave that for your CCIE studies. And the final tiebreaker is to answer the question, which of my neighbors has the lowest IP address? The neighbor with the lowest IP address will be the preferred next hop. In other words, the preferred path. And if you count all of these up, there are 13 criteria that we could examine. That's a lot to remember, and I've heard a variety of memory aids to help you memorize a specific set of path selection parameters, but in this video, I wanted to share what I consider to be the simplest memory aid that I've run across. It's my favorite, and it does a great job of helping us remember some of the key components in this BGP path selection decision. It's not totally comprehensive, it doesn't get into route reflector considerations, but it does help us memorize the BGP path selection parameters that are used the vast majority of the time. Now, by the way, I didn't make up this memory aid, it's just one of the more popular BGP memory aids out there, and I wanted to share it with you. It's an acrostic, and it goes like this. We love oranges, as oranges mean pure refreshment. I'll say that one again. We love oranges, as oranges mean pure refreshment. Here's what that acrostic means. The W in we reminds us of the W in wait. We love, the L in love reminds us of the L in local preference. We love oranges, the O in oranges reminds us of the O in originate. We love oranges as, the AS in as reminds us of the AS path length. We love oranges as oranges, the O in this second instance of the word oranges reminds us of the O in origin type. We love oranges as oranges mean. Here, the M in mean reminds us of the M in the multi-exit discriminator, the MED. We love oranges as oranges mean pure. The P in pure reminds us of the P in paths. And finally, we love oranges as oranges mean pure refreshment. With the R, we jump down to the router ID. And this might be a simpler table for you to work with and memorize. We love oranges as oranges mean pure refreshment. This is still a sizable list though. So the question is, what do we as network engineers in the real world need to do typically to influence path selection for our enterprise routers going out to the internet? And how do we influence internet routers as they come into our enterprise network? It really boils down to 4 parameters that we typically use to modify on our router. After all, we probably don't have the luxury of configuring the ISP's routers. We have to keep the configuration local to our router. And here are the 4 most common path attributes that we'll typically use. They are wait, local preference, autonomous system path length, and the MED. And that's a look at how BGP makes its path selection decision.